All right, let's talk about something we've all faced. You're in a test, you're cruising along, and then, bam, you hit the problems on ages section. For a lot of us, that's where the anxiety kicks in, right? But what if I told you that in the next few minutes, we're going to flip that feeling completely on its head?
I mean, look at this thing. 18 years ago, a father was 3 times as old. It's just a wall of words, right? It's designed to look complicated. It's totally normal to see this and just think, oh boy. But hang on, because the solution is way simpler than it looks. So what's the secret? Well, here it is. What if these problems aren't about complex math at all, but about simple translation? That's the big idea here. The moment you stop seeing them as a math test and start seeing them as a logic puzzle, everything clicks. Your job isn't to be a math whiz. It's to be a code breaker.
And honestly, this is the only skill you really need. You just have to read the question really carefully and turn the words into equations. The sources on this are super clear. These problems can be, and I'm not kidding, extremely easy if you just pay attention. Everything you need is hiding in plain sight. Okay, so if we're going to be code breakers, we need a decoder ring, right? That's what we're doing now. We're building our toolkit, our cheat sheet, for turning these confusing sentences into math that actually makes sense. And check this out. This is the entire code. It's kind of funny how simple it is. If you see after n years, you just add n. If it says n years ago, well, you subtract n. Ratios, that a to b thing, just call them ax and bx. And n times is old, that's just multiplication. That's basically it. The whole secret boils down to these 4 simple rules.
All right, we've got our decoder ring. Now it's time to actually use it. Let's circle back to that scary-looking problem from the beginning and see what happens when we apply these rules. You're going to love how fast it unravels.
So here it is again. But does it look a little less intimidating now? It should, because it's not a big scary paragraph anymore. Now you can see it for what it is. 2 separate clues. One about the present and one about the past. We can tackle them one at a time.
Okay, first things first, let's handle the present. We'll just call the father's age F and the son's age S. Simple enough. The sentence says, now the father is only twice as old as the son. Okay, twice just means multiply by 2. And boom, F equals 2S. There's our first equation. See? Easy. All right, now for the second clue. 18 years ago? Okay, our decoder ring says that just means the father was F minus 18 and the son was S minus 18. And back then the father was 3 times as old. So the father's past age, F minus 18, equals 3 times the son's past age, S minus 18. And just like that, we have our second equation. No sweat. So look where we are now. We took that whole messy paragraph and boiled it down to these 2 clean equations. All that confusing language is gone. And since we know from the first equation that F is the exact same thing as 2S, the next move is pretty obvious, right? We just swap F in the second equation for 2S. And from here on out, it's just basic algebra. We plug in 2S where F was, we multiply that 3 into the parentheses on the right side, then it's just a matter of shuffling things around, get the S's on one side, get the numbers on the other, a little quick math, and there it is. S equals 36. The son is 36 years old right now. Okay, once we know the son's age, finding the father's is a piece of cake. We just jump back to that first super simple equation we made, F equals 2S. Plug in 36 for S, and we get 72. So the father is 72. We've got both their ages. But hold on. Don't celebrate just yet. This is a classic trap. You always have to double-check what the question is actually asking for. It didn't ask for their individual ages. It asked for the sum of their ages. So we take 36, add 72, and we get our final answer, 108. That's it. That big, complex word problem, solved. And all we had to do was translate it piece by piece. Now, the cool thing is, this whole translation idea isn't just for this one specific type of problem. You can think of it like a new superpower, and it works on all sorts of different age questions. Let me show you what I mean. Okay, check out this wording. Ajay is as much elder than Vijay as he is younger to Kunal. That sounds like a riddle, doesn't it? But let's just translate it. It's really just a fancy way of saying that Ajay's age is smack dab in the middle of Vijay's and Kunal's. The difference in age between Kunal and Ajay is the exact same as the difference between Ajay and Vijay. See? A confusing sentence becomes a simple, balanced equation.
And this way of thinking works for all of them. It doesn't matter if the problem starts talking about averages, or brings in 3, 4, 5 people, or even uses fractions and percentages. The fundamental strategy never changes. Slow down, look for the relationships between the words, and translate them into math you can actually solve. So here's the bottom line. The most important thing to remember is this. Age problems are language puzzles. They are not math nightmares. Your best weapon isn't a calculator, it's translation. The next time one pops up, don't think, oh no, math. Think, okay, what's the code here?
And really, that's the big idea I want to leave you with. Now that you know how to decode the language of time, what other complex problems out there are just waiting to be translated? How many other things that seem tough are really just simple ideas hidden behind confusing words? What else can you crack the code on?